We are live.
Okay, great. Well, thank you very much for attending session 5A, Human and Robotic Exploration, Moon 2. So it's our second session focused on the moon specifically. We have 4 great talks, all focused primarily on rover activities. So that's quite near and dear to my heart. So I'm pretty excited about this. So our first speaker is Pierre-Lucas Aubin-Fournier from Concordia University, and his talk is on vibration-based wheel terrain slip detection for skid steer rovers. So Pierre-Lucas, I see you. Perfect. Do you want to share your screen? And just so we're clear for all the speakers, we give about 15 minutes for the talk and then 5 minutes for questions. I'll give you a notice once you hit the 15 minutes. And then it starts eating into the question time, if that makes sense. Okay, take it away, Pierre-Lucas.
You're muted, Pierre.
Yeah, we don't hear you.
Muted. Okay, I'm no longer muted now. All right, so my research as part of my master's degree at Concordia University deals with the slip estimation from vibration data captured on skid steer rovers. So the problem statement that we have is that terrain wheel slip is essentially a precursor to soil entrapment. Soil entrapment is generally undesirable with rovers. Here we have an image from the Spirit rover on Mars, which was ultimately lost due to soil entrapment. And here we have a short animated GIF of an opportunity also suffering from Mars. So the ability to detect slip events before they lead to soil entrapment is thus quite valuable. Visual odometry can be used to measure slip with some delays and usually with high CPU costs. So these slip detection delays can increase sinkage and entrapment risks. So my research goals were to develop the ability to measure and detect elevated slip events from vibration data with a focus on relying mainly and possibly only on the vibration data itself, having a quick detection of medium slip events, targeting under 1 second delay, having a high reliability to try and minimize false negatives, and focus on low computing solutions to make it very suitable for micro rovers that don't necessarily have very high computing on board. And finally, one of the goals was to develop and test the system with both lab and field data. So some existing literature that I found was that some vibration-based systems have been demonstrated in the past, but for all of them, the wheel torque measurements are necessary for the system to function properly. And this can be an issue since while it's quite common to have a wheel torque measurement device on a test bed or on some research rover, in actual missions, the wheel torque measurement is not always available, at least not directly with a force torque sensor at the wheel. And also in the research that I found, most of them dealt mainly with lab setups, and only one had field data, a system that was proven with field data. So the progress so far for my research, I've started with some lab testing, which I've done in our facilities here at Concordia University using a Husky. And what we do is essentially we induce slip in the Husky's movement with an overhead gantry. We've captured data sets for 0 to 90% slip generated in this way. And we've done so for different soil preparations, so compact soil and loose soil. And all the vibration data was captured at 400 Hertz. And here we have a short video that shows how a test would run. So naturally, in the constraints of the sandbox we're using, only linear motions were used in this testing campaign. Next, we did some field testing, which was accomplished at the CSA's Marsyard facility. And in these tests, we induced slip with a larger rover, essentially holding back the Husky with a rope assembly. Again, here we captured data sets for 0 to 90% slip. And here, given the wide expanse of the facility, we captured a few different data sets. So for straight motions, some turns, and slopes as well. And for slopes, we captured both low slip slopes, which would be a good case where we're climbing a slope and very little slip is seen. So the slope climb is successful. And high slip slopes where the slope is much trickier and maybe we don't quite achieve the climb, or the climb is achieved with high difficulty. And here again, we captured the data at 400 Hertz. And here we have a short video of, again, what like this would look like, or what it did look like since it happened. So here we have some sample data that we've captured, essentially at 10% slip for a straight motion at 5 centimeter per second. We have a nice comparison of the lab test here, which shows very little vibration, because since 10% slip is quite a low value of slip, that is a normal value for motions in loose soil. And the field test at the CSA Marsyard, which also shows only a little bit of transitional vibrations. Here we have higher slip test data. So at 30% slip, we start seeing large amounts of vibrations appear, both in the lab test and the field test. So we see a little bit of difference between the two. This could be due to the fact that at the field test, the soil is much more humid than in the lab. So the soil dynamics are a little bit different. And here at 50% slip, we see generally that the vibrations tend to peak around 50% slip. So, and that's true in both the lab test and the field test. So we did some frequency domain analysis to try to see if there were dominant frequencies in these vibrations, and we found that there is essentially resonant frequencies at around 16 to 18 hertz, which dominate the spectrum. So on the left here we have the frequency analysis with the linear scale. And on the right, we have a logarithmic scale. And we can also see at the top that for slip values under 11% or 11% or under, there are very few vibrations. Whereas when slip passes about the 15% threshold, so between 15 and 25%, we have a significant vibration which appears, and the peak of vibrations typically happen between 25 to 65%. Interestingly, at very high slip, so more than 65% slip, we see much less vibration than, so the vibrations tend to taper down as the slip goes into higher values. So yeah, linear amplitude, log amplitude. So here we have we've looked at the RMS value of the vibrations, and we can see that essentially what I mentioned just now, where the vibrations are more or less non-existent under around 10% slip, and they rapidly increase from 10% until about 40%, and around 40% is the peak, and higher values have less vibration. Interestingly, also on this graph, we can see we have tests at 5 centimeter per second and at 20 centimeter per second. So as would be expected, when the rover is traveling at a faster speed, the vibrations are much higher. So having some sort of scaling to bring vibrations seen at different speeds onto on a same, to be able to compare them properly, some scaling would be necessary according to rover speed. And here we can one of the things we were also gathering during our tests was the DC current consumed by the motors of the rover, and we can see that as slip increases, the DC current consumption increases linearly. So in order to try to detect slip events, we looked at a classification system, and in terms of low computing solutions, SVMs, support vector machines, are typically interesting. So here we have a quick overview of the process we used, where we essentially separate our data sets into training, validation, and testing segments. And then we, using 2-second segments of vibration, we try to classify them in either very little slip, so negligible slip, or significant slip. And we have some preliminary result, which we've done mainly using lab test data. So with slip between 10 to 20%, we have data sets at each percent, and for 20 to 90%, we have 8 sets, so a less specific. We were mostly interested in the transition zone between 10 to 20%. So by training with the slip data at 10 to 30% and testing with the full slip range, we have some ROC curves which indicate the performance of our system, with the slip threshold being set at 15%, 17%, or 20%. So with the slip threshold at 15%, we can see that the RC curve indicates high performance for our classification system. However, when we change the threshold towards 17 and 20, we get reduced performance, which would seem to be mainly due to unbalanced training data. So this is something we need to work on and improve with potentially more test data. Some of the future work that we would be interested in is to scale the vibration data according to either wheel speed or motor current, to try to be able to compare different movement speeds on a same basis. Next, we would be interested in investigating unsupervised classification methods. Another thing which would be interesting would be to try to link the vibrations from the turning motion slip to the linear slip in skid steer rovers. So when skid steer rovers turn, the wheels experience a certain amount of slip, and from what we've seen in our field test data, the same kind of vibrations that are seen at higher slip values in linear motions appear at certain turn radii. So being able to train a system on vibration data from turns would be interesting if it could be tied to slip event detection in linear motions. And also in turns, there are essentially 2 different types of slip. There is the slip of each individual wheel, which is a lateral slip, and there's also angular slip in a turning motion, which could also be interesting to detect. And finally, testing our system with various rover sizes and different wheel materials or types would be interesting to make sure that the this system essentially can be generalized to other rovers than the Husky. And that would be my presentation. If you have any questions, you can also email me at this email. And I'd like to acknowledge our partners, so the CSA, for providing access to their Mars Yard facility, and Mission Control Space Services for their bi-weekly technical consultation meetings.
Great. Thank you, Pierre-Lucas. If there's any questions from the attendees, please put them in the chat window. I am certainly happy to ask Pierre-Lucas all kinds of questions, given our involvement and my interest in this topic, but I certainly want to encourage questions from the audience as well. But we have a couple of minutes, so maybe I'll start. Pierre-Lucas, how is, it wasn't, and maybe I missed this, so apologies for that, but how is slip measured in your test campaign?
You are right. I did not mention this. I don't think it's visible in the pictures I have either. Essentially, what we have is two different things. So for the, let me scroll back to my pictures. So for the tests in the lab, this is taking a while to scroll. So in the lab, essentially, we are we're generating the slip values using the speed on the gantry. So we essentially command a fixed value of slip, and then that's what we use. That's what we tag our data set with. For the field tests, so same thing for the tests where we use the larger rover. We just it's a fixed value of slip. But then for the slopes and for the turn data sets, we used a total station, which is actually a rangefinder device. Yeah. And we have a prism mounted to the Husky rover, which can be tracked by the total station.
Interesting. Okay, so I guess where I was going with this, so it's this effectively drawbar pull tests that you're doing here with the large rover and the small rover. So what I'm curious to know, with total station will give you fairly high frequency slip information or odometry, right, or your pose. When you're taking these kind of results and developing classification schemes, and then looking ahead to implementing this as a kind of an early warning system for an embedding event, do you see any challenges in taking, the kind of practical realities of slip detection on board a rover, and either averaging over time to get those measurements versus the, I guess, speed at which you need to be able to detect sort of I guess you're using vibration, but the speed at which you need to be able to detect something before it becomes a problem. I guess you see what I'm getting at there.
Yeah. Well, in terms of challenges, I would say one of the main things that I've been maybe a little worried about is that, so for all our tests, we've gathered the vibration data at 400 Hertz, which is a rather high frequency at which to pull an accelerometer. So one of my worries was that potentially in actual missions, they might not have such high frequency access to the accelerometer data. And so we might need to make sure that our system can work with a reduced frequency data. So that's one worry, I would say.
Yeah, that makes sense. That makes sense. Okay, great. Well, we're coming up on the 20-minute mark now. So thank you very much for your presentation, Pierre-Lucas. It was really interesting. And we will go to our next speaker. Sorry, I just need to look up here. So our next speaker is, I believe, someone probably in the same lab as you, I'm assuming. So this is Adriana Daca from Concordia University. And the title of this presentation is Predicting Wheel Performance in Lunar Gravity on Cohesionless and Cohesive Soils. Right, yes, I see your, okay, I see your screen and I see you. Perfect.
Okay, great, perfect. Thank you for the introduction. Let me just configure my screen here. Okay, so hi everyone, I'm Adriana Daca. I'm a PhD candidate at Concordia University, and yes, I'm in the same lab as Pierre-Lucas. And today I'll be presenting my research looking at how we can predict wheel performance in lunar gravity on cohesionless and cohesive soils. So hopefully you see my second slide now. So the motivation for this work stems from the fact that one of the major challenges that planetary exploration rovers face today is the negotiation of difficult terrain. And on the Moon and Mars, this can consist of loose granular regolith. On the left side of the slide, you can see the lunar roving vehicle. And during the Apollo 15 mission, one of its wheels became stuck, and the astronauts actually had to pick up and move the vehicle in order to fix the problem. And on the right, we have the wheels of NASA's Spirit rover, which Pierre also showed in his presentation, and it similarly got stuck in loose soil. And as there were no astronauts there to free it, this sadly led to the end of its mission after attempting to free it for many months. So why is it that we couldn't figure out how to free Spirit? Well, one of the most common mobility testing methods is reduced weight testing. And in this method, the weight of the test rover is altered in order to emulate the gravitational acceleration of its destination. So for example, here on the left, we have Scarecrow, which is it's a 3/8 mass version of the Curiosity rover, and it mimics the weight that Curiosity would have on Mars. And on the right is an image showing gravity offload testing, where a cable, I'm not sure if you can see the cable, but it's here pulling up on the rover. And this is to simulate lunar gravity, which is, of course, approximately 1/6 of Earth's gravity. And this type of testing method does accurately represent the effect of gravity on the weight of the rover, but what about the effect of gravity on the response of the soil? This is an important factor that is not always studied. And the next two testing methods we're going to look at do attempt to account for the effect of reduced gravity on the soil behavior in addition to the effect of reduced gravity on the rover. So the second method we will be looking at today involves matching soil testing instrument response through soil simulant design. So the lunar soil simulant GRC1 was designed to replicate the cone penetrometer response, the cone penetrometer readings taken during the Apollo missions. And now a cone penetrometer is an instrument that measures the pressure required for insertion of a cone on a long shaft into the ground. And in the design of GRC1, it was assumed that replicating the cone penetrometer response of lunar soil would also replicate its response to vehicle loading. So in other words, the same wheel performance is expected in different gravity levels as long as the cone penetrometer response is equivalent. And this assumption had not actually been validated with any reduced gravity data. And the third method that we'll be discussing today involves scaling laws. Granular scaling laws, or GSL, are a framework for predicting wheel performance based on a set of scaling relations. So for example, they allow you to predict the performance of a larger wheel based on tests with a smaller wheel, or to predict wheel performance in one gravity level based on tests in another gravity level. And this is analogous to scaled tests that are used in aerodynamics, for example, with dimensionless numbers such as the Reynolds number. And prior to the results I'm about to present, the gravity variant version of these scaling laws had not been experimentally validated, and they were only validated using discrete element method simulations. So here, shown here is an example of a smaller wheel that can be used in 1G to predict tests with a larger wheel in lunar G using these scaling laws. And I'll show you those results later on. So we've been systematically evaluating these three testing methods using the experimental setup shown here. This specialized robotic test bed was designed to meet the constraints imposed by reduced gravity parabolic flights. On the left, you can see the test bed configured for wheel testing. We have an instrumented sandbox with a force torque sensor that measures the forces and torques on the wheel as it drives through the sand. For example, drawbar pull, the force with which a wheel pushes or pulls itself in its direction of motion. And we also have a potentiometer that measures sinkage, or the vertical displacement of the wheel beneath the soil surface. And on the right, the test bed is shown in its cone penetrometer test configuration. And again, the cone penetrometer measures the pressure required for insertion of this cone into the sand. And the cone penetrometer was used to match the response of the terrain for method 2, which is matching soil testing instrument response. And this testbed is also capable of automated soil preparation, and it prepares the soil to a repeatable state between tests. Okay, so in the first parabolic flight campaign with this testbed, method 1, which I introduced earlier, reduced weight testing, was evaluated using an ExoMars prototype wheel in the Martian soil simulant ES2. And wheel experiments in Lunar G, Martian G, and 1G were performed at equal wheel load, and it was found that method 1 overestimates wheel performance. So compared to Lunar G, the 1G tests using method 1 overestimated the net traction or drawbar pull by about 25%, and they underestimated the sinkage by about 30%. So higher drawbar pull and lower sinkage correspond to better wheel performance, which is what we saw in the 1G tests. And similar results were seen when comparing 1G and Martian G tests, although to a slightly lesser extent. So since the effect of gravity on the soil particles was essentially isolated in these experiments, it was concluded that this is an important factor that needs to be considered in mobility testing because the performance in reduced G was worse than what we saw in the 1G test at equal wheel load. Now, before I go into the second parabolic flight campaign results, I'm just going to briefly introduce the granular scaling law equations and test inputs. So the GSL equation that we implemented is shown here, and it is modified from the original form that was proposed in the literature a little bit. And it is a 3-output, 5-input unspecified function, and we called our modified function omega. And the outputs are, all the inputs and outputs are non-dimensional quantities. So we have in the outputs, non-dimensional drawbar pull term, a sinkage term, a power term. And then on the input side, we have non-dimensional time, a wheel shape function, non-dimensional gravity, a kind of size term, and a non-dimensional velocity term. Now, if we define 3 scalars down here, Q, R, and S, to scale the gravity, the radius, and the mass. So capital L here is the characteristic length. In this case, it's the wheel radius. So these 3 scalars can be chosen arbitrarily, and the inputs and outputs for the test pair will look like this. So I'm just going to give you a quick explanation and example, and it will all make sense. So for example, if you look at the dimensionless velocity term and you substitute in the test 2 inputs, so you would have Q multiplying G on the bottom here and R multiplying L on the bottom. And then you see that the velocity is scaled by the square root of Q times the square root of R as well. So all those scaling factors, the Q's and R's will cancel out, and you'll have the same inputs to the unspecified function for each test. So this is a valid scaling pair. And for our experiments, we chose the scaling parameters such that the test inputs and outputs basically would fit within the operating limits of our test bed in terms of like the torque required and the load on the wheel and everything like that. So yes, for the 1G experiments in the second parabolic flight campaign, we had a wheel with half of the radius, and that's the one that I showed earlier. And yes, the other changes are also shown here. So moving on to a little bit more of a description of the second parabolic flight campaign. So in this flight campaign, rigid wheels were used to evaluate methods 2 and 3. And just to reiterate, method 2 was matching the soil's cone penetrometer response. And for this, we were looking at the metric capital G. So this is not gravity, this is the cone index gradient. So basically, we had a lower density soil in 1G, and we had a higher density soil in Lunar G, and we matched the cone penetrometer measurement for those. And actually, we saw that the drawbar pull in 1G was 44% higher than the one in Lunar G, even though the soil was much looser. And the sinkage was also lower in 1G compared to Lunar G. So this method actually overestimates the wheel performance as well as method 1. And method 3, on the other hand, the granular scaling laws, they underestimate wheel performance by less than 10% error on each metric. And so this means it's a more conservative method. So I'm going to show you just some more detailed results from that flight campaign. So shown here, we have the actual Lunar G experiments, the blue lines, and then the granular scaling law prediction in green. And then we have the method 2, we called it here the equal G method. The capital G, as a reminder, is the cone index gradient. That method is shown in red. So each line here is an average of 3 or 4 experimental repeats. And then the kind of faded color around the line is the 95% confidence interval. And the left plot shows the drawbar pull to weight ratio at 20% slip. And then on the right is the same for 70% slip. So you can see that the granular scaling law prediction is much more accurate, especially at 20% slip. And then at 70% slip, it's more conservative. Whereas the equal G prediction is, like I said earlier, overestimating the drawbar pull. And then looking at the sinkage results, again, we have 20% slip on the left and 70% slip on the right. And again, we can see that the granular scaling laws are much more accurate, especially at 20% slip. And again, it's more conservative at 70% slip, where it's overestimating the sinkage. So the sinkage in 1G was actually higher than what we saw in Lunar G. And then for the equal G method, again, it's overestimating the performance in that it's underestimating the sinkage. So what are we going to do next? Future work. Recall that the results I just presented from the second parabolic flight campaign were obtained using the soil GRC1. Now, GRC1 is cohesionless, whereas the actual lunar regolith is more angular, as you can see in the image here. So it has more interlocking forces between particles and more cohesion, and therefore it has higher shear strength. And the current best estimate for lunar soil cohesion is about 0.1 to 1 kilopascals, which is not very high, but it's definitely not zero. And based on our results from the second parabolic flight campaign, we do believe that method 2, matching the soil's cone penetrometer response, it may be more accurate when comparing GRC1 in 1G to a higher shear strength soil in Lunar G. So that's what we're going to do next. And additionally, for method 3, the granular scaling laws, if the soil is cohesive, there's actually an additional constraint that has been proposed recently, where the radius ratio must be the inverse of the gravity ratio. So to explain that, for example, in 1G, since the gravity on Earth is 6 times higher than lunar gravity, the wheel radius used in 1G for testing must be 1/6 of the radius of the actual wheel that's operating in Lunar G. And since testing a 1/6 scaled rover might not be very practical or desirable, we are now going to test these scaling laws in a mildly cohesive soil to determine how much error is introduced if we ignore this constraint. And just to give a little bit more info about the cohesion constraint, this new term shown here in the kind of teal color, it was proposed to account for cohesion. So we have the cohesion stress here on the bottom, and then this is like a type of critical density for the material. And this term has only been validated using DEM simulations thus far. So recall that in order for a pair of tests to follow the scaling laws, the inputs to this unspecified function must be the same for a pair of tests. So the cohesion and the critical density of the material are not really something that we can easily control. So let's just pretend we can't change those. So if we want to have the test to be a valid scaling pair, then we need to have this Q multiplying the G and the R multiplying the L, they need to cancel out. So basically we have a new constraint that's added to the parameter space. Q must be 1/R. So as I said before, if we're testing in 1G with the goal of matching Lunar G results, Q would be 6. So then R would need to be 1/6. So this means, again, that if we're considering cohesion, the wheel radius on Earth would need to be 1/6 of the wheel radius on the Moon. And we are planning to evaluate this constraint experimentally by measuring performance of single wheels with different diameters, driving through Exolith Labs Lunar Mare simulant #1, so LMS1, and the cohesion of loose LMS1 has been measured to be about 0.34 kilopascals, so pretty well fits into the range of lunar soil cohesion. And test, we have a 1/6 radius wheel. So test with the 1/6 radius wheel will follow the cohesion constraint, and they'll be compared to the test with the 1/2 radius wheel, which does not follow the cohesion constraint. So yes, we can estimate the error introduced by ignoring this constraint by comparing the results of these tests. And then again, we'll have the full size wheel in lunar gravity for comparison as well. So in summary, these 3 techniques for 1G rover mobility testing have been evaluated. None of them is perfect so far, but method 3, the granular scaling loss, has shown a lot of promise. And we're currently working to evaluate methods 2 and 3 in a mildly cohesive soil simulant with the short-term goal of developing 1G testing guidelines. However, in the meantime, before these guidelines are established, there's definitely still value in testing wheels for upcoming lunar missions on reduced gravity parabolic flights. So that is it for me. Here are the references I cited throughout the presentation. And thank you so much for listening. Do you have any questions?
All right. Thank you very much, Adriana. So I'd encourage anyone in the audience to ask questions in the chat window. I don't see any right now, so that's okay. I did my PhD in wheel design, so I could ask you some questions.
Okay.
My first one is a kind of a practical one. In the test bed developed and used in parabolic flights, how is the soil sort of prepared at each test? And I guess at each parabola, I assume that the soil would, how does that actually work? I'm curious.
Right, so we actually, between each parabola, we prepare the soil in 1G. So yeah, we try to, we ask the pilots to keep the plane at straight and level flight, but it's actually kind of descending during that phase. Anyway, so yeah, the soil is just prepared between each parabola.
Kind of manually, like, okay.
Oh no, it's done. Yeah, good question. Sorry, that's the actual question you were probably asking. So it's done with air jets, like blowing through the bottom of the soil. And there's like, we have a plastic porous sheet at the bottom that kind of diffuses the air evenly throughout the soil. So it's like lifting and fluidizing. And then after that, there's a vibration step. So it compacts it to like a level, repeatable state.
Interesting. Okay. Cool platform. There is a question here in the chat window. I'm not sure if you can see it there, but by Marie-Josée Potvin at CSA. So she says, you reduce the radius, but seem to keep the same width for the wheel. Should this need to be parametrized also? Extremely interesting, by the way.
Thank you. And thank you for the question. Yes, the wheel width, yes, we did keep it. Well, it's not exactly constant. I think these 2 wheels, I'm not sure if you can see the small writing. They're a bit less wide, but this is done. Well, I guess I can show this equation. It's actually helpful to keep the wheel wider because it allows us to have a higher mass onto the wheel, a load on the wheel, because it's very difficult to control the wheel load and have such a small load. So we opted to have a slightly higher load. It's just the way that the equations work. We can have a higher wheel load with the wheel width. So you can see here the D is the width of the wheel, and that's kind of scales proportionally with the mass that's allowed on the wheel. So that is why we have the width not scaling linearly with the other ones.
Okay, great. We got one more minute. I had another question for you. You were talking about the 1/6 scaling of the radius of the wheel. Could you explain that a bit more? I was trying to like wrap my head around, are you implying that if you're sort of doing some ground testing on the Earth, if you want to scale for gravity rather than changing the weight of the rover, you could just scale the radius of the wheel to have sort of equivalent performance that you would then see on the moon. Is that what you were sort of getting at?
Yes. Well, it's not exactly equivalent performance. You can see here the outputs are scaled, so you would need to like do some calculation. So for example, this is some test inputs for the 1/6 radius wheel, and you can see like the angular velocity would be 6 times faster, but the actual velocity of the rover would be the same. But the drawbar pull is 9 times lower, the sinkage is 6 times lower, and the power required is 9 times lower. So you can basically use these scaling laws to apply these scaling factors to your results with the tiny rover, and it should match up with the full rover.
Gotcha.
In lunar gravity. Yeah.
Okay. Interesting. All right. Well, thank you very much, Adriana. It was a great presentation and good questions from the audience. We will go to our next presenter. Our next presenter is, thanks. Joel Moore from Ryerson University. And the presentation is entitled Simulation of a Sparse Bundle Adjustment Solution for Rover Navigation. All right, I see you, Joel. And if you could just bring up your screen, perfect. I will jump off. Yep. Take it away.
Okay. You can still see my screen?
Yep, looks good.
All right. So hi, my name is Joel Moore. I'm a PhD student from Ryerson University, working in the Space Avionics and Instrumentation Lab under the supervision of Dr. John Enright. Today I'm talking about a simulation of a sparse bundle adjustment solution for rover navigation. So one of the goals of our work has been to study the long-range performance of ego motion techniques under controlled conditions. To this end, we've developed a simulator that tracks randomly generated landmarks for motion estimation. This simulation is a tool that can be utilized to examine the effect of stereo configurations and additional system parameters on the generated solution. And it also allows for the determination of sources of error within any of the gathered data. One of the fundamental challenges in autonomous robotics is ego motion, which is the task of recovering the three-dimensional motion of a camera relative to its environment. Motion estimation on Earth is a simple task with the use of a GPS, which can provide nearly instantaneous localization information to a very high degree of accuracy. However, for locations like GPS-denied locations like the Moon and Mars, motion estimation becomes more problematic. So a technique called visual odometry is used, which is a vision-based system that utilizes onboard cameras attached to the rover, and by capturing sequential images, landmark features are detected and used to form an estimation of the rover movement. The basic VO pipeline shown here begins with capturing and processing a set of images from a pair of stereo cameras. So you have a left and a right camera, and they're exposed at the same time and rectified and any other post-processing that needs to be done. Sorry, not post-processing, just processing. Features are detected in each image using algorithms like SIFT and SURF, and stereo matching is used to determine common landmark positions. And after 2 consecutive stereo pairs have been matched, features can be tracked between frames. So due to the nature of the intensity-based approach, however, for both detection and matching, there's the established set of temporally matched features will contain outliers. So to remove these erroneous points, outlier detection algorithms such as RANSAC is used to reject outlier feature tracks. And finally, both the rover pose and three-dimensional locations for the landmarks are solved using a nonlinear numerical approach. So the left figure here shows, my pointer, shows a single step in the visual odometry pipeline. So the red dots indicate the projection of the landmark position in the left and right stereo pair at a time k-1 right here, while the blue dots represent the landmark projection at time k. After an arbitrary rotation of phi and it's a 3 by 1 vector phi and translation rho of the cameras. The association of features in the individual stereo pairs provides depth information, while the temporal feature association, i.e. the association across time steps, provides a basis for motion estimation by analyzing the apparent 2D motion in the image plane. And the right image here is a sample image showing the stereo features extracted from 2 temporally consecutive images. The features located in frame K-1 are shown in green, and their corresponding temporal features are, at time K, are shown in red. And the blue lines indicate the optical flow, which represents the general motion between images. So sparse bundle adjustment is, in order to solve the system, we implement a method called sparse bundle adjustment, which is a standard refinement method of optimizing a visual reconstruction. So frame-to-frame bundle adjustment is used to simultaneously determine the translation and rotation of the cameras, as well as the location of the landmarks between an initial stereo pair at time K-1 and second pair at time K. So this translation and rotation information is stored within the state vector along with the landmark positions. And the state model used to describe the rover here is defined by the homogeneous transforms at both time steps consisting of translation rho and rotation matrix C from the top eccentric to camera frame, and the landmark position J in the top eccentric frame. The origin of this T0, the estimation frame, is defined to have the same orientation as the locally defined top eccentric frame at time 0. So bundle adjustment is a nonlinear least squared problem that provides a maximum likelihood estimate to both the camera parameters and the computed three-dimensional landmark positions to minimize the squared Malhalla-Novus distance. The framework for this objective function was developed by Lambert et al. And is composed by the linearized inclinometer, sun sensor, and stereo feature errors, which are due to a small perturbation, and their corresponding covariance T. However, to obtain a global motion estimate, the sun sensor and inclinometer both require a current estimate of the vehicle orientation relative to the top eccentric frame, which is why a prior error term is added to the objective function. To determine an estimate for the state at time K, an iterative Gauss-Newton optimization technique is used to minimize the objective function in the neighborhood of the current estimate by solving for the required updates to the state at each iteration of the Gauss-Newton algorithm. So a simulation was developed to examine the underlying mechanisms that control the behavior of the visual odometry solution. Using the sparse bundle adjustment framework, stereo parameters can be adjusted to observe the effect different stereo configurations have on the estimation. Variables can be tuned to examine their effect on the system while maintaining control over other parameters. For example, this allows us to simulate landmark positions without the need to simulate constraints such as terrain and factors like illumination and surface texture. And an additional constraint to this simulation was the absence of a feature bias within the point generation. So a lack of terrain within the simulation means that the points are generated uniformly within the field of view of the cameras. So the field test data, there's usually an oblique bias to these features, which means that features on the ground, they appear closer to the rover, and features that are further away, they are above the horizon, are further away. So there's a bias to the features themselves. So because of that, that's one other aspect that could be, it's right now it's a constraint. It isn't considered for the simulation. But yeah, so the main input to the simulation is the GPS ground truth for a for a data set. However, there are also a number of parameters that can be tuned to change the system configuration. So these include varying the camera field of view, stereo camera baseline, camera rotation, so the actual physical rotation of the cameras, point generation density, and the working range. The output for this simulation is an estimate of the rover orientation in the form of a quaternion and a position vector at each time step. To simulate the unaided stereo camera data, a point cloud is created that contains three-dimensional landmark positions along an arbitrary trajectory. And you can see the arbitrary trajectory is just this dotted line, is this solid black line here. For a large traversal, a significant amount of point data is generated, so a simple method of restricting the visible space was developed. For each rover position, a spherical volume is generated, these red spheres here, those spheres, at a fixed distance from the camera frame origin, where the working volume radius r and working distance h are also parameters that can be tuned or changed. The generated volumes are then combined to create they trace out a tubular volume along the dotted line, which is considered the visible space for the entire trajectory. The tube is the restricted volume in which all of the point data is generated, represented here by the green dots, and its center is the curve traced by the motion of the spherical volume centers. So the region of interest defined by the tube is then sliced into cylindrical volumes with faces defined by the location of the spherical centers, and the number of points generated in each slice are a function of the slice thickness and the density parameter. That way, if there's larger steps between frames, the number of points is then dependent on that step between frames. So to simulate feature detection, normally you would be using a feature detection algorithm that would be looking at intensity-based or using intensity-based matching. However, for this, we've generated the points, and now we just want to do a pseudo feature detection where points within the common field of view, indicated by the green area here, it's actually a green volume, they must be identified within that volume. To minimize the computational cost, the search for features is restricted to only the volumes located within view of the cameras. So the black dots represent all of the available volumes, and the red dots indicate volumes that are visible up to the camera within a maximum defined range. Similarly, feature matching is conducted by determining the intersection of point IDs between features in the left and right fields of view. And this method for feature matching is conducted across sequential frames to simulate temporal feature tracking. And for a very large trajectory, for example, the one that we use to analyze the simulation, there's a large number of frames. For example, the one is over a 10-kilometer trajectory, so it has 40,000 frames. So the idea is to minimize the search area so you don't have to really care about the additional data when you're not actually looking at it. So the number of segments is dependent on the number of frames in the trajectory, and depending on the time step between frames for each segment of for the data set that we used, roughly 10% of the total volumes were visible at each given time step. So although the volume may be within view of the cameras, some of the points may also be generated outside the common field of view. So this is a zoomed in variation of it, but you can see that some of the points that are generated within the volume may lie outside. For example, in this volume at the beginning may lie outside the field of view. For the aided visual odometry simulation, the sun sensor and inclinometer data are generated using a simulated true orientation at each time step for the inclinometer, and a perturbation is applied to the gravity vector calculated from the true orientation. Likewise, the sun sensor, a true solar ephemeris, is calculated over the simulation time, and artificial measurements are generated by perturbing the sun direction vector that was calculated using the true orientation vector in ephemeris. So the numerical solution is beneficial because it allows you to test stereo configurations without needing a physical rover. And it's also useful for validating experimental data. So to develop a reliable simulation, we use the Devon Island data set, which was collected by Fergal et al. In the Canadian High Arctic, which consists of a 10-kilometer trajectory divided into 23 segments, as seen here in the left image. And this shows the GPS ground truth that was used that was generated from the entire trajectory. The right image shows the pushcart rover that was used to collect the data using multiple sensors, including stereo cameras, an inclinometer, sun sensor, and a GPS. Further data was collected in our lab using a rover platform that we developed. This data will be used as an alternative trajectory to examine the performance of the simulation. One of the sail data sets that was gathered in Toronto is shown here. It was just around a city block over a distance of just under half a kilometer. And it's shown here, and this is our rover that we developed. It has the same sensors as the pushcart that I just mentioned. So using the data, a comparison of the Devon Island and simulated data for what's called segment 0 using the sparse bundle adjustment framework was generated. The total path length for this segment was 412 meters. And again, this is just one of the 23 segments over the 10-kilometer trajectory. So this first figure here shows the comparison between the unaided, i.e. pure VO solution, utilizing both observational and simulated stereo data. This means that there's no simulated data for the inclinometer and sun sensor or Devon Island. Those sensors were not included in the unaided analysis. Though there is a variation in the estimate using the simulated data, the performance of the simulation is comparable to that of the estimate for the Devon Island data, with a final difference in error of about 30 centimeters. So these two figures here show the comparison between the VO solution using an individual sensor. So the top right shows just the sun sensor, and the bottom left is just the inclinometer. And as seen,
Joel, you're just a bit over time. You're into the question period now, but that's okay. You have a couple minutes left.
Okay, I'll make it quick then. So as seen with the unaided, there is a variation over the trajectory. However, the overall trend is comparable to the non-simulated. And finally, this figure shows the comparison between the fully aided, i.e. using both sensors, along with the stereo cameras. And we can see that there's a notable decrease in error over the trajectory for the simulated data, due mainly because of the combined effect of the inclinometer and sun sensor. And this resulted in a final error of about 4.1 meters. Lastly, the other simulation that we ran was to examine the effect of front-facing versus side-facing camera, so changing the camera configuration. So this figure here shows the 2 time steps where the black dots are landmark positions. And the landmarks can be better localized because of their positional uncertainty is reduced. You can see the positional uncertainty between side-facing and forward-facing camera configurations. So to examine this effect, this has on the performance of the solution, a simulation was conducted utilizing a forward-facing camera. And this figure here shows the results of the simulation, where the red line is the front-facing camera and the blue line is the side-facing camera. And the overall error growth for the side-facing is notably smaller, with an 82% reduction in error, which is expected from this figure you can see here. So in conclusion, we successfully produced a simulation that can be used to generate synthetic data along an arbitrary trajectory, as well as a tool to examine the effect of different stereo parameters on the VO system. This was achieved through a comparison of the sparse bundle adjustment solution using the Devon Island measurement data. And future work will include increased simulation fidelity by incorporating, illumination changes, terrain, feature bias into the measurements, as well as gathering further urban data sets to have a more urban analog for our simulation. So thank you. I think that is time for questions, if there is still time.
Great. Thanks, Joel. We should be moving on to the next presentation, although I feel like I'll give a moment for anyone who wishes to put any questions in the chat window. And if they don't, maybe I'll ask you just a kind of a quick one here. Yep. What do you expect? How do you expect the performance when you look at kind of the lunar environment and sort of the, lack of features, so to speak, and the, different illumination conditions? How do you expect that performance to kind of go in that sort of environment?
Right. So the Devon Island data set was a Mars analog data set. It was conducted in the high Arctic, so there were very limited features, but it does definitely have an effect on the pure VO solution. There is a much higher error growth, a superlinear error growth, when you have less features. So in an urban environment, for example, there's a lot more features that you might be able to use, assuming it's a dynamic environment. So on the moon, there's definitely going to be a higher VO error growth. So you're going to rely on the additional sensors to help reduce that error growth over time. Great.
Well, thanks a lot, Joel, for your really great presentation. So we'll go to the next presenter now, who I believe is my colleague, Kaizad. Do you want to share your video? So Kaizad is a business and product development manager here at Mission Control. We work closely together. And he will be presenting on, his presentation is called Enabling AI and Autonomous Robotics, a demonstration for the Emirates Lunar mission. All right, Kaizad, I'll let you take it away from here.
Cool. Thanks, Mick. Just quick audio check. Let me know if you're hearing me properly.
Yep, sound good.
Okay, awesome. Yeah, good to be here. Hi, everyone. Definitely looking forward to Cassie Astro getting back to person again so I can meet everyone face to face. Hi, everyone. My name is Kaizad, and I work at Mission Control with Mick, as mentioned, a Canadian space exploration and robotics company. And happy to share an overview of our next generation mission operations software and our flight software technologies that help enable AI and autonomous robotics. And of course, in the context of our participation in the upcoming Emirates lunar mission. Thanks to the Canadian Space Agency for providing financial support to enable this capability demonstration. And of course, to all our partners as seen on this slide as we go to the moon and beyond. So at Mission Control, we develop software technologies that add autonomous capabilities and streamline operations for planetary science missions, focusing on mission operations, onboard autonomy, and AI. And as a young and growing company based in Ottawa, we're all very excited to build cutting-edge technologies to power the next wave of lunar exploration, and very passionate to bring students and the public along on our journey as we're committed to inspiring the next generation. Our goal, as you probably get through all of these slides, is really to help make missions more efficient and productive using smart approaches with software and operations techniques, and enable scientists and other operators bring home the key information they're looking for so that they can meet their objectives more efficiently. And in this talk, I'll walk through how we do that with some of our innovative software technologies and to help achieve this goal for lunar rover missions in particular. So it's an exciting time for lunar exploration, as all of you know. Several surface missions are scheduled to fly to the moon in the next few years. But there are going to be many challenges, like the limitations with onboard data processing and the capabilities of these platforms, and in particular, the short duration of these missions that'll last within a single lunar day, which is 10 to 12 days on Earth. Consider this type of mission architecture where a rover has very limited onboard autonomy. Essentially, everything that the rover does is operated by ground control on Earth, And this relies on a highly constrained communications link to get data. Could be a few hundred kilobits per second at most. Operators have to spend a lot of time in analysis and making decisions. And for safety, a micro-rover's step command may only be about 1 or 2 meters. And all of this culminates in a lot of idle time and effectively a slow mission speed. And because we're kind of entering this new paradigm of commercial missions, this will have an adverse impact on science return and mission value for the types of missions we're going to be seeing in the near future. So how can we improve on this? So to address these challenges and help maximize the return of these missions, we're developing software technologies to help rovers operate more independently from Earth. And with technologies for detecting obstacles, planning trajectories, micro-rovers can go to where the operators want them to faster, safer, and more efficiently. Our science autonomy tools will allow a rover to autonomously identify and target geological features with onboard instruments. Some of these technologies require a high-performance flight computer, which can be feasible for small rovers, but also pose additional challenges. And so in certain scenarios, we can take a flexible edge computing approach to have technologies integrated on nearby spacecraft, such as the lander or a satellite, so that the rover can still benefit from these technologies in the flight segment and still avoid or minimize the latency and bottlenecks from Earth-centric operations. And in fact, this is an approach that we're going to be demonstrating as part of the Emirates lunar mission. Ultimately, once again, this is all towards the goal of trying to maximize the science return and value of these short duration missions, especially in this new commercial model. So how do we get there? So if we agree that automating certain tasks that a rover can do more independently and allowing operators to focus on more critical and strategic tasks, an autonomous lunar rover must simply be able to perceive its environment, understand how it interacts with that environment, and then make intelligent decisions based on commands from operators on Earth. So the technologies that we're developing to enable this range from classifying surface features on the surface of the moon, building a map of the rover surroundings, intelligently modeling hazards, as well as its ability to do traverses safely and efficiently, and then making its own decisions such as path planning and following, and autonomously targeting its instruments to collect data of specific features. Now, I'll just give a quick overview of how our terrain classifier works. It's designed to use deep learning techniques to classify surface features like rocks and craters in images taken by the rover. And these data products can then be aggregated onto a map to build a bigger picture of the rover's traverse, which can be used for many types of scenarios and applications. It provides useful geologic context for science investigations. The map can be used on board a rover for rover path planning, as well as picking out where a particular science sensor may want to collect data, so on and so forth. On the ground segment, these data products can be used to speed up the process of annotating images and help distributed teams share and analyze information and make decisions faster. Speeding up the process of annotating images reduces workload in fast tactical cycles if the rover is continuously driving or making quick stops. The teams at NASA JPL are using these approaches for Mars rovers in a kind of a different concept of operations. And we're kind of at a stage now where we're figuring out how to do this for lunar mission operation cycles that are much more quicker and rapid. So classified features can be used to create these digital object models, which can then be used in many ways within an operations context. So for example, a user can quickly pick an object to then share with colleagues across different consoles, submitting an instrument targeting request, for example. These types of objects can also then be quickly cataloged into a database that can then enable intelligent feature-based query during real-time mission operations, as well as after the mission. For example, a scientist might want to pick out a specific feature like a small degraded crater on a particular day in a particular geographic box. Other data can also then be assigned to this type of object model from multiple instruments. All of this enables statistical analysis much faster and in a more streamlined fashion. And so those types of data products can be quite useful for mission operations. Over the last year, we've been busy integrating this deep learning terrain classifier onto a flight computer ready for our mission launch next year. Here are some early results of our prototyping work using images that we had downloaded and labeled from the Chinese Chang'e 3 and 4 missions on the right side of my screen, and then using some images that we developed as part of a high volume data set at our own indoor lunar testbed. This is a critical step we're working out with our science teams in order to make sure that these data products are useful for science team members in lunar missions. And more progress will be made, of course, in the upcoming year as we get closer to our mission. In what we expect to be the first demonstration of deep learning on the surface of the moon, our terrain classifier will be processing images from the Rashid microrover and then returning the results down to Earth, where the data products will be used to support advanced navigation techniques and scientific research. And our mission control software platform will help enable streamlined operations for our distributed team, so useful for anyone that's participating remotely. And of course, we're very excited to plan some fun and creative initiatives to bring the students and public along in our journey. So this is just a quick high-level architecture of the demonstration and how this fits into the Emirates lunar mission. As the Rashid microrover roams the surface and streams back images to Earth via the iSpace lander, our AI-based terrain classifier that's going to be embedded on the lander on a Xiphos Q7 flight computer will be processing these images. And as part of this first lunar demonstration, the resulting data products will not be used directly in the flight segment, but will be downlinked to be used in the ground segment, where our team will support navigation and other operations activities. We will also demonstrate the use of our mission control software, our cloud-based operations platform, to enable live participation of remote participants, in particular the members of our Canadian science team. And we're also continuing to develop a cutting-edge novelty detection system that uses deep learning methods, but with a different approach to identify novel or high-value targets that are rare or unexpected or unseen before. And this is ongoing work we're doing partly in partnership with Concordia University, Dr. Christoph Skonechna, as well as Western with Dr. Ken McIsaac. Novelty detection is a very exciting and emerging area, largely motivated from challenges with operating Mars rovers. And we're now developing it for applications on the moon. And our participation in the Emirates lunar mission will give us a wealth of information on strategies to implement this in future missions. As part of our lunar surface demonstration, we're also going to be investigating how autonomously identifying these types of lunar surface features will support modeling wheel slip hazards, modeling how much energy a rover spends while driving, and then using these models to generate safe and efficient traverses for rovers. And this is part of an ongoing research project, again, in collaboration with Dr. Chris Konechna at Concordia. And we're excited to advance this for use in future lunar rover missions. Also, another exciting science investigation that we're going to be conducting and supporting with our science team is the use of our AI to then advance data processing for multiple types of instruments and sensors. And so we're going to be looking at data from the micro camera on the Rashid rover and studying how our AI can then be used to classify distinct regolith particle types. Once again, the goal of this is to significantly alleviate the quantity of data that needs to be downlinked during real-time operation cycles. So if you can quickly characterize these types of data on board and find the key information that a scientist might be looking for, that'll help streamline the operations and make things more efficient. Beyond our flight demo and advancing these applications I've just mentioned to support rovers and payloads, we're also excited to demonstrate our core product offering to the space exploration community, our cloud-based mission control software platform. So for missions in space and also for testing on Earth, this makes it easy for operators in distributed teams to interface with robotic systems and payloads. And we've designed a web-based app that allows operators to drive a rover, operate science instruments, interact with different tools and visualize data products and more. And this also comes with a software development kit that makes it easier for spacecraft teams to integrate their systems and enable end-to-end data connectivity. As some of you might have seen earlier, I'm not sure, our Lunar analog testbed is a really fun place where we get to test technologies and validate operation strategies, and also give live presentations as my colleague Mick did today. We're offering a unique capability these days for anyone with an internet connection to run on-demand lunar analog missions by simply logging into our web-based browser and driving our rover around to test the different types of lunar mission scenarios that people are working on. This has been incredibly useful for our science team partners, especially on multiple projects, as they're trying to get more detailed operations procedures going. So if you'd like to see this in action, feel free to reach out to me or Mick, and we'd be happy to run a quick demo for you. Last but not least, as part of our lunar demonstration and all our ongoing initiatives, we love to give students an opportunity to immerse themselves in planetary rover operations through our Mission Control Academy. We've done this since the start of our company and enabled hundreds of students to get a feel for what it's like to operate a real space mission by teaching them how to plan a mission and then letting them drive a rover in an analog Mars or Moon environment. I'd like to end this presentation just by underscoring that this is really a new paradigm of space exploration that we're entering. And our company, Mission Control, we're eager to power this next wave of missions to the moon and beyond with software technologies that can help make these missions safer and more productive. And of course, helping Canada strengthen its reputation as a leading country in space robotics in the global community. Some of these technologies that I've mentioned will be reaching TRL 9 by 2023 as we execute on this demonstration with the Emirates lunar mission. And so if you're looking for these types of technologies for your next project, we'd love to talk more about that. Last point I'll make is that we published a couple of papers recently at the IAC conference, International Astronautical Congress, as well as the AIAA Ascend conference that goes into more details about the terrain classifier, novelty detection, and our indoor lunar testbed. So if anyone wants to get more information, I'm happy to provide those papers as well. Okay, that's it. Thanks for listening. And of course, please reach out to me with any questions or comments and follow us on social media.
Awesome. Thanks, Kaizad. Great presentation. I can ask you questions, although I probably know the answers. So anyone who has any questions, we still have a minute or two here in the session before we end off. So please use the chat window. But if not, then maybe I'll kind of put myself in the shoes of a student watching this and ask, this seems cool. Are you hiring?
We're hiring for so many things, I can't even keep track.
What kind of skill sets do we look for at Mission Control? I guess maybe it could be a useful thing to share with the audience.
Yeah, well, we're a software-focused company, so chiefly we're hiring for software developers from a range of different perspectives. So we're building technologies on an embedded flight computer on a web-based operation stack. So those are the kinds of environments that we're looking for, people with skills on embedded systems, as well as working on web technologies. And beyond that, we're doing a lot of cool work, as you probably saw, on developing applications that go onto those systems. So if you're working on a robotics project, computer vision, machine learning, those could be quite useful for us, and especially in some scenarios, if you're working with a particular type of payload and have ideas on how to improve automated operations for those types of payloads, that could be useful for us too.
Very nice. Very nice. All right. Well, we came up on the hour now. It's 3 o'clock. So I believe that's it for our current session, if I'm not mistaken. So thank you very much to all the speakers who joined us in this session. And I will be chairing the next session, but with a less focus on the moon. But I'll join you all here in about 15 minutes or so. So thanks, Kaizad. Thanks, everyone. And have a lovely afternoon.